Okay, so one of the uses of these significant digits is figuring out how to round things so that, figuring out how to round things so that you don't have misleading results. So when you're adding numbers together, the general rule, you'll see fairly frequently in your homework from now on, round to an appropriate number of significant digits or round appropriately or something along those lines. And when you see those rules, we're assuming what we mean by that is that you're going to be applying these rounding rules. It's not rounding to the 10th place or something like that, but now it's going to be figuring out, you have to figure out where you're going to be rounding from a lot of the problems here on out. So when we're adding and subtracting numbers, these measurement numbers, what we do, the general rule, is to keep the lowest precision. That is, whichever one has the, this is to the 10th of a second, this is to the 10th of a second, this is the 100th of a second. Both of these are lower precision because they only go to the nearest 10th of a second. So that means when we add these numbers together, we need to round it to the nearest 10th of a second. We essentially lose some precision when we add them together. 4.1 plus 3.5 plus 1.27 gives us 8.87 if we were to just add them kind of without thinking about it. But we need to round this off to 8.9 seconds. So you may wonder, why in the world would I round? That would inherently make this less accurate, less precise also. So the problem with writing 8.87 seconds is that by having this 7 here, you're saying that you know that this number is accurate to the nearest 100th of a second. But we don't know it's accurate to the nearest 100th of a second because each of these were only rounded to the nearest 10th of a second. And so we're rounding this number off to show roughly what our error is going to be on this. Each of these numbers, this could be anywhere from 4.05 seconds to 4.15 seconds. This could be anywhere from 3.45 seconds to 3.55 seconds. This one would have to be 1.265 to 1. I guess I'm saying to the fives, but whatever. You get the point. It's somewhere within these ranges. This gives us a full 10th of a second range. That gives us a 10th of a second range. This one only gives us a 100th of a second range. But when we're adding them together, we're going to just maintain that 10th of a second range there. So rounding to the lowest precision number. The same thing goes on this one. 7.425. 7.425 minus 3.5 rounds, the exact value before rounding is 3.925. But again, this is implying more precision than we actually have. We actually need to round this off to the nearest 10th, so I'm going to go ahead and cut that stuff off, and we're going to call this approximately 3.9 inches. On this next example, you can see we have a 1/10 of a pound here, we have 3/4 of a pound here, and a 1/10 of a pound here. What we're going to do is we're just going to more or less ignore the fact that the 3/4 of a pound, it's actually a less accurate measurement than the 1/10 of a pound, because this is going down to quarters. We're just going to keep the, what does this say? It says the usual procedure is to round the precision of the original decimal measurements. So the original decimal measurements, meaning these two. Those are both to the nearest 1/10 of a pound. So we'll go ahead and round this one to the nearest 1/10 of a pound. So we get 3.2 pounds plus 1.75. I'm writing it as a decimal, 1 3/4, instead of 1 plus 3/4 because it's easier. Plus 2.4. This gives us 7.35. And we're going to round this off to 7.4 pounds. Like I said, rounding to the nearest 1/10 of a pound. Now you may be wondering, when we're rounding these, I said that this could be anywhere from 4.05 up to 4.15. This, we have a 1/10 of a second variation here, a 1/10 of a second variation here, and let's say we're adding, 6 different numbers that all have a 1/10 of a second variation. If we were consistently low on every single one of those numbers, then the measurement we come up with here would actually be implying, the errors would essentially build up, and we could get it in an entirely different, a significantly different number. But what we're doing when we're doing these is we're kind of assuming 4.1 seconds, we're assuming that, well, I mean, yes, that number is between 4.05 and 4.15. We're assuming this 4.1 because it's right smack dab in the middle. And we're kind of making the assumption that half the numbers are going to be bigger and half the numbers are going to be smaller than the actual thing we're talking about, and that those errors will, for the most part, cancel each other out.